Did you know that geologists might be able to tell where you went on vacation just by analysing the sand stuck in your backpack? And without ever actually seeing that sand.
What are you going to do that based on?
X-ray diffraction.
A method that uses a so-called XRD scanner. You put in finely ground soil and sand samples, and it returns a graph like this. Apparently, such a diffractogram reveals exactly what minerals are inside the sample. Online mineral libraries, containing data on over 10,000 different minerals, can help to identify what's there. The elements that show up depend on the environmental conditions the sand has been exposed to. Arjan Dijkstra is an earth materials specialist, meaning he creates a lot of these scans.
Typically 100 a year, so not huge numbers, but I've also seen lots of these scans that other people collected. Yeah, often students come to me with scans.
Let's just say crazy numbers. So here's the real test. Has he become a living version of the mineral library? One that can not only identify the minerals, but actually determine where they came from.
Interesting challenge, yeah.
That's what we're about to find out in this series.
Let's go.
Okay.
In this episode, Emma's adventure to some rare green beach leaves her with an unintentional souvenir. Stubborn sand hidden in her backpack. The sand has been ground and put through the XRD. Now we're ready to present Arjan with its diffractogram. Can he deduce her holiday destination from it?
This one's easy, I think. I think I recognize those big peaks there at 36 or 37. There's one of my favorite minerals. There's olivine. I would want to use the computer now to work out which peaks are not olivine, but I think almost all of them are olivine. So tell me that this is a nice green sand. Yeah, no, I did my PhD on olivine, right? So this one I should be able to recognize, right? And there's not many beaches that produce that consists of olivine, right? Also, olivine is quite an unstable mineral. It forms in volcanic rocks, in some basaltic rocks that are full of olivine. They're called piccrites. We don't see it very much, but it's at the same time it's the most common mineral on our planet. But that's because most of the mantle, the Earth mantle, so the bit beneath the crust, consists of olivine. So if we go here 35 kilometers beneath our feet, we come into the mantle. So we're out of the crust, we're into the mantle. And there, olivine is the dominant mineral, all the way to what we call the mantle transition zone at about 480 so kilometers. So if you think about that in terms of the volume of our planet, that's the biggest volume. So by that reasoning, olivine is the most common mineral. We don't find it a lot on the Earth's surface though, but volcanic rocks can bring up bits of the Earth mantle and can therefore be full of little clusters of olivine. We call them xenoliths or olivine nodules. But also in some basaltic magmas, olivine can crystallize again, typically very high temperature basaltic magmas that are produced by melting of the mantle at quite deep levels, at 100 kilometers or so. They have a lot of magnesium in the magma, and when they then crystallize at the Earth's surface in a lava flow, they crystallize olivine. It's also, by the way, a mineral we do a lot of research on at the UT, because actually olivine can react with CO2, and it's a perfect mineral to turn it into magnesium carbonate, to actually sequester, to actually fixate CO2 from the atmosphere. And that's a way to fix CO2 on geological timescales. So it's a mineral that we also research quite a lot here at the UT. But yeah, beautiful mineral. It also consists you can also find it as a gemstone variety, then it's called peridot. It's beautiful green, olive green, hence the name.
We share your enthusiasm, Arjan, but we're not looking for a gift shop to buy this wonderful gemstone. Do you have any idea where this sand from Emma's backpack might have come from?
Olivine breaks down quite quickly, so we're again right on the volcano, I would say. I can only think of the beaches on Hawaii, the famous green beaches, that we see on Hawaii. There is another beach I know in Norway, but it's not a tourist destination, so I would say Hawaii. So tell me, for this one, hopefully for my confidence that I'm right, that this is a green beach at Hawaii. well, if this is not going to be green, then I will, I will eat my hand lens.
He'd better be right.
This is nice and green, right? Beautiful olivine, the olive green, shiny, transparent crystals. There's only very few places in the world where you find this. So I said Hawaii, right? So this is going to be again a sample from Hawaii. I fair chance that this is right. Yay!
Well done.
Yes.
And with that, this series concludes with a 3 out of 4 score. From behind your screens, can we get an applause for Arjan Dijkstra, an expert geologist, master in deduction, and above all, a truly passionate and extremely enthusiastic researcher. Now, if you're curious to learn more about the process of creating these diffractograms, join us again next time for the bonus episode in which we join Katrin as she walks us through the step-by-step procedure of sample preparation.